welcome to the second video lecture accompanying Chapter 1. All right, well this lecture starts with Section 1.2. We're going to talk about the timeline of the universe, or the history of the universe. We want to talk about where did the universe come from, and understanding how much time there's been and how that compares to the human experience, right? Okay. All right, so how did we come to be? So there's some key stages here. We have the birth of the universe, key moments in the Big Bang. This is the topic of cosmology. Then we kind of have this idea about how galaxies are formed, different types of galaxies. There have been sort of generations of galaxies over the about 15 billion years of the entire universe. And then we can focus in on more recent events like the formation of a solar system like ours. And eventually, after the sun is formed and the planets become less volatile and there's less asteroids crashing into the planets, then we have a stable planet like ours with a stable atmosphere and a magnetic field that can exist. Okay? So that's kind of the key moments, taking progressively less time. All right. Except for maybe the Big Bang being a very fast event. All right. So how do our lifetimes compare to the age of the universe? Okay, so the cosmic calendar, this is kind of a fun idea, is a scale on which we compress the history of the universe into 1 year. So in doing that, we can see there's kind of this idea, right? We have the 12 months, and we think of January 1st as the Big Bang. That's the moment that the universe came to be. So then our galaxy would have been formed in February, all right? Much, much later, we have the formation of Earth in September, life first existing on Earth in late September, so early September, the planets formed. A few hundred million years later, the fossil record tells us there was first life. And eventually, there's a lot of stuff that continues to happen in terms of our own planet, evolving as far as life is concerned through September to November, all the way up through December. And then a lot of key moments happen all in December. These are the things we know as like the dinosaurs, which would happen on December 26th, amazingly enough. It's the rise of the dinosaurs. And then I think this is probably maybe the most telltale thing. The dinosaurs, which are around for hundreds of millions of years, they evolved on December 26th and went extinct on the 30th. All right? I mean, to put that in perspective, humans evolved about 2.5 million years ago, 3.5 million years ago, kind of depending on what you define as an actual human. And, well, if we were to go extinct now, if we were to, like, say, wipe ourselves out with a nuclear winter, then our entire existence would just be, well, a day, basically, on the cosmic calendar. Okay? All right, and then if we actually zoom in on the last day of the last month of the cosmic calendar, we can see, and this is quite interesting, right, that by 9 p.m. we have early humanids, modern humans at 11:58 p.m. Wow, right? Wow. So that really puts it in perspective, So, I mean, we're not even around for a day, right? The 2.5 million years is just a few minutes in the scale of things, right? And then all of civilization, things from the earliest agriculture to the pyramids, built thousands of years ago, that just happens in the final seconds of the final day of the final month of the cosmic calendar. Oh. All right. So, how do we come to be? Well, the matter in our bodies comes from the Big Bang. So everything that exists in the universe started with the Big Bang. When the Big Bang happened, there was only hydrogen and helium. There's some key reasons that when the theory and the background radiation, the telltale examples that we have of the direct evidence that we have of the Big Bang, it tells us that it only created hydrogen and helium. So all the other heavier elements came from stars. All right? So what happens is the other elements were constructed from hydrogen and helium in stars, inside their cores, and then recycled into new star systems, including our star system. So the key idea, and we'll talk about this later, we talk about the life cycle of stars, is large stars in particular form heavier elements. When the stars explode, they form even heavier elements, and that explosion ejects those trace amounts of heavier elements out into space. Eventually, they can then become part of balls of rock like our own planet, and then they're left on the surface of that planet amazingly. So when someone mines gold, they're mining gold that was created in a cataclysmic event of an exploding star or stars crashing together millions or billions of years ago, because that's the only place it could have come from. Right? It wasn't created here on Earth. There's no fusion occurring here on Earth that would come anywhere close to creating something as powerful or as heavy as gold. All right, and we already talked about how our lifetimes compare to the age of the universe. We saw that all of civilization, right, just was a few seconds. So if you think of a human lifetime of, say, generously 100 years, then that's just going to be a tiny fraction of a single second in the cosmic calendar. All right, so let's then consider how Earth is moving through space and how galaxies move. All right, this is section 1.3. We moved past timeline, and now we're getting into the movement of kind of how space isn't stagnant. The galaxies are swirling disk composed of those hundreds of billions of stars. Of course, our solar system is spinning, rotating. There's a lot of angular motion in space. All right, and we're going to finish all of chapter 1 in this video lecture. Okay, so one of our first movements is, well, the fact that Earth is spinning about its own axis. Okay, so it rotates about its own axis once per day. So that's kind of the first realization we have. We sit at our table at home, or we sit at our desk at home. Maybe we're sitting on our couch with our phone watching this video on double speed, whatever it may be. You seem like you're at rest, but of course you're not at rest because the Earth is spinning, and you can get an idea how fast you're spinning if you are at a latitude like where we are at, or a little bit further south. You're moving at about 1,100 kilometers per hour. That's actually a very fast speed. And that is your speed relative to the fixed axis that runs through the center of Earth, because the Earth is essentially a ball that's spinning about that fixed axis due to leftover angular motion from the formation of the solar system. You're moving a little bit faster on the equator. That's actually why it's always more cost effective to launch rockets at lower latitudes, because everything weighs slightly less at the equator, because everyone is getting thrown off the planet by a tiny amount. Now, you might be like, wait, you're going to be throwing out the planet? But what about gravity? Well, that's the thing. The centripetal force, just like when you, say, ride a ride at an amusement park and you get spun around and pushed up against a wall, that's the centripetal force. Well, that centripetal force, or the perception of it called the centrifugal force, is counteracting gravity, but it's much weaker. In fact, this effect at the equator would only account in a 0.03 or 0.3% change in your weight. So 0.3% lighter at the equator. All right? And that's the lightest you would be, because as you move up to the pole, well, now there's no centripetal force, so you would just be your full weight, which is determined by gravity, which is determined by the size and mass of the Earth. Okay? But we'll talk about kind of the origins of gravity and something called the universal law of gravity in a later chapter. But that's not the only motion. Meanwhile, of course, the Earth orbits the sun. Right? We know that takes a full year for the Earth to make that orbit. The average distance from the sun has a special name. It's called an AU. AU stands for astronomical unit. All right, this is one of the key terms you've already seen, but it's a good one to focus on, astronomical unit. Okay? And that corresponds in kilometers to about 150 million kilometers. That's our average distance from the sun. All right? So that means we have to make a circle that has a radius of 150 million kilometers every 365 days, right? That means we're actually moving quite fast. Tens of thousands of miles per hour is how fast we're moving around the sun. All right. So the Earth rotates in the same direction it orbits counterclockwise as viewed from above from the North Pole. All right. So there's actually everything in our solar system, almost everything in our solar system is spinning in the same counterclockwise direction. That makes sense because everything was formed together, and all that swirling gas that formed the sun and then leftover particles that formed the planets, that was all part of the same original motion. And there are some exceptions. There are some astronomers think collisions and other key events that led to some things that spin the opposite direction. There's a moon of Uranus that orbits the opposite direction. Venus appears to be completely upside down, so it's spinning clockwise. And so there are some exceptions, but generally, as a rule, everything is either orbiting and spinning in the counterclockwise direction. The vast majority of moons, planets, all the motion in the solar system. Okay. Meanwhile, a final bit of motion. Our star is orbiting the center of the galaxy with a orbital radius of 27,000 light years. Remember, 1 light year is about 9 trillion kilometers. So now we have a very, very big circle. And that entire orbit of our star around the center of the galaxy, the galactic center, that takes about 230 million years. Okay, so kind of like on a fossil scale, 230 million years ago was when the dinosaurs were around, right? So in that time, we've gone all the way around the galaxy. And it does have some real effects as we pass through different sections of the galaxy, because not all the galaxy is moving at the same rate. It's more like a swirling liquid mass rather than a solid object spinning. We actually do pass through different regions of radiation and so on. It's quite fascinating. But that ends up giving us a speed relative to the center of the galaxy at 70,000 kilometers per hour. So okay, so there we go. That's our final relative speed, right? But no, of course, the galaxy itself is moving relative to other galaxies. The entire universe is expanding, and we'll learn later that it's expanding and accelerating, which means it's speeding up in its expansion, which is a huge mystery. All right. So our sun moves randomly relative to other stars in the local solar neighborhood, right? So the stars are kind of getting pulled and pushed relative to each other as the whole galaxy is moving. All right. All right. So how is our sun moving in the Milky Way? Well, looking from the side, a more detailed study of the Milky Way's rotation reveals one of the greatest mysteries in astronomy. Okay, and this is going to hint at the idea of dark matter, not dark energy, which is a separate proposed explanation of a mystery. But the idea is that, I'll stay on the side for just a second, the idea is that we're moving faster than we should be. Because when we look at the solar system, the further planets move slower, the closer planets move faster. The fastest planet in our solar system is Mercury, which is the planet closest to the sun. The slowest moving planet is Neptune, which is the planet that is furthest from the sun. Right? And every planet closer than Neptune moves a little bit faster than Neptune. And that's because it's being tugged on with a greater gravitational pull, because the closer you are to a gravitational source like the sun, the greater the pull. So it should be that this galactic center should have the greater pull. But we find that the speed of stars is all the same. Our sun is moving at the same speed as, V for velocity, these are the same. Even though this, by conventional logic and by the ideas that we see in by the laws of physics that we thought we understood, and we do see in our own solar system, this star here should be faster, but it's not. It's the same speed as our star, which is much further out on one of the arms of our spiral galaxy. And the only explanation for that is that there's an envelope of mysterious dark matter that doesn't interact with light, that surrounds galaxies, not just our galaxy. Okay, well, we'll talk about that briefly in one of the last chapters. And as I said, galaxies themselves are carried along with the expansion of the universe. Right? And we'll talk about Hubble, this name here, because Hubble was the one that discovered that. We'll get into Hubble's law and its importance for measuring distances. All right, all galaxies outside of our local group of galaxies, we saw that when we talked about our cosmic address, are moving away from us. The more distant the galaxy, the faster it is racing away. Conclusion, we live in an expanding universe. And you might say, wait, if all galaxies are moving away from us, except for those ones that are kind of trapped in and embraced with us, our local cluster, does that mean we're special? Are we the center of the universe if everything's moving away from us? No, every galaxy would experience every other galaxy moving away from it. Or at least every cluster of galaxies would experience every other cluster of galaxies moving away from it. It's really no different than imagining air bubbles in bread. If I had a loaf of bread and I had it, and I was going to bake that bread, and these were the initial air bubbles, and the bread remained the same bread but just got bigger, right? So here's the same loaf of bread. All the air bubbles would be further away from each other. They all would have moved away from each other. And that's what's happening with our universe and the galaxies moving away from each other. So every galaxy perceives every other galaxy moving away from it. Okay? So are we ever sitting still? Absolutely not. No way. There's no such thing as a fixed still point in the universe. In fact, 100 years ago, leading up to the discovery of special relativity, or the proposal of special relativity by Einstein, this big turning moment in physics and astronomy and cosmology and understanding these fundamental laws and breaking fundamental laws and having new ones be proposed, that up until that point, we thought maybe there was such a thing as a fixed rest point in the universe. They called it the cosmic ether. It was the idea that there was some sort of permanent web in the universe and everything was moving relative to it. But it doesn't exist. All right? As far as we know. So how is Earth moving through space? I think we've summarized this quite well. You can look through these slides on your own. All right? So finally, the human adventure of astronomy. How has the study of astronomy affected human history? Right? So there's some key moments here in history. Has in the progression of astronomy. The Copernican revolution showed that Earth was not the center of the universe. Okay, we'll talk about this more in chapter 3. Then there was a key moment when Newton's laws were proposed. These are the laws of motion and gravity. So we'll talk about universal gravity, and we'll talk about the rules of motion. There's 3 laws. They're called Newton's 3 laws. And so these are key points, and these are really only about a generation apart, Copernicus to Newton. So this was a point. Now, this is a very Eurocentric view. I mean, the ancient Greeks had some key ideas, but they got lost. We entered a region of history where this information wasn't passed on. Certainly in the Arab world and China, they had understandings of the Earth not being the center of the universe. They had understandings of Earth being a circular body and so on. But as far as kind of our modern, society, our global society built on European imperialism, that's kind of where we can look to a turning point is with the Copernican revolution, and then this codifying of laws with Newton. This moment of understanding the physical world in much more depth than we had for hundreds of years. Okay, and this all took place in the 1500s, and then the 1400s. Okay. Newton's laws laid the foundation of the Industrial Revolution. Again, to put perspective there in terms of history, for those of you that are history buffs. Modern discoveries are continuing to expand our cosmic perspective. And really, the rate of discoveries is just increasing. You look at every century, there's just more discoveries per year, more groundbreaking things. We're just understanding so much more. And throughout history, astronomy has provided an expanded perspective on Earth. So it might be far away, distant stuff. It might seem like it doesn't apply to everyday life. But it gives us a perspective. It gives us something to think of. What is our role? What is our future? Right? Are we just going to be wiped out by an asteroid someday, or will we populate the stars? And if we will, how? How do we even make sense of our place and our ultimate role? Okay. All right. Well, that's a good thought to end on. Thank you for tuning into this second video accompanying Chapter 1. And take a look out for the videos accompanying Chapter 2 from Cosmic Perspectives, Fundamentals. All right. Thank you again.